Oh, someone asked a question on Piazza. Will there be a stream next Friday? That's an excellent question. I was going to, because, I mean, every day is basically the same as every other day for me at this point. I don't mind doing one. I could also like move it to Thursday if that's easier for folks. They're always recorded, so you can watch them later if you can't make it on that actual day. So if you have strong preferences of like whether I should or should not do it, then let me know. Actually, I would love your opinions on that. Can't believe it's week 10 already. All right, so for this game, we have, if you've played it, you know how it works. It's a really fun game, really interesting, like, dynamic, and the rules are fairly simple, but the gameplay can be really complicated. So the game's called Hanabi. It's a card game, and the deck has 5 suits, or there is actually also a 6th that you can play with, but we're just going to consider 5 for now. And the cards in each suit, there are multiple copies of some of them. So there are 3 1s, 2 2s, 2 3s, 2 4s, and a 5 in each suit. So there's 10 cards per suit, 50 cards total in the deck. And you get a hand 4 or 5 cards, but you don't see your own cards. That's the key difference with this game than many card games. So you actually hold your cards like fanned like this, but facing away from you. So everyone else can see your cards, and you can see everyone else's cards, but you cannot see your own. The actual gameplay itself, the goal is to get, piles 1, 2, 3, 4, 5 in as many suits as possible. But the idea is you can give other players clues about the cards that they hold. So you could tell them these are all your red cards, or these are all your 2s, or whatever. And the goal, again, is to create those piles. But the key thing is that you cannot see your own cards. You can only see everybody else's. And let's just imagine at the very start, we have no information about anything at all, like we can't see anything that anybody has. We can define some variables. So we'll just let X equal the number of 1s that you have in your hand, and Y equal the number of red cards in your hand. And in this case, we'll imagine how many people are playing with, you happen to have 4 cards. That obviously the X and the Y there can be anywhere from 0 to 4, because you could have no 1s all the way up to all 1s. You could have no red cards all the way up to 4 red cards. Both of those or any of those are possible. And so what we can do is find the joint probability function, little f of xy, as follows. And it's this big table here. And you'll notice that some of those values are colored in different colors, and I'm going to explain how we calculated each of them. Because it's a pretty complicated distribution. Like, this isn't any of the distributions that we've named. Like, the hypergeometric is a little bit involved because we're selecting cards from this deck without replacement and not caring about the order. So it has some element of hypergeometricness to it. But it's not just like 2 hypergeometric random variables that we can then multiply those probabilities together, because it doesn't quite work the same way. It's possible for a card to be both 1 and red. So it's not quite just as simple as taking 2 hypergeometric random variables and combining them together. So let's see how we can calculate some of the values in this table. Why don't we start with the red ones? So if we're looking at these values here, if I get my marker here, that's saying that X is equal to 0. So in other words, we have no 1s in our hand. In the deck as a whole, if it's playing with 5 suits, then there are 15 1s. So actually, we only care about how many of your 4 cards are red versus not red. We're basically saying, let's ignore all the 1s. And then we want to say, okay, out of those cards, how many are red and how many are non-red? So if we want f of 0, 0 here, that's saying we want to have no 1s and no reds, that's all. So we need to choose 0 of the 7 red cards that are not 1s, and all 4 of the cards that we want to choose are from the 28 non-1, non-red cards. That's what I meant. And then, of course, as a whole, the denominator for every single one of the values in this distribution is going to be 50 choose 4, which is just the total number of ways to get 4 cards from the deck of 50. If we want f of 0, 1, that means, again, no 1s and 1 red card, exactly. The way to do that is we want 1 of the 7 red cards, that's not a 1, and then 3 of the 28 cards that are not red and not 1s. And that gives us that probability there. And similarly, we can calculate the rest of that column. So there we go. That gives us that set of values. Next, I want to look at the y equals 0 row. So this set of values right here. So in this case, similarly, we're now saying that if y is equal to 0, that means you have no red cards in your hand. So we can't have any of those 10 red cards. And so we're basically looking only at the other 40 cards in the deck and thinking about, out of those, how many of those 4 cards that you have are ones or not ones, again, given that none of them are red. So we can do that. We can say, all right, if we want f of 1, 0, that means 1, 1 and no red cards. There are 12 possible cards that are ones and not red, and we want one of those. And then the other 3 cards have to be among the other non-red, non-ones in the deck. And then again, we're always dividing by 52's 4, and we can calculate that similarly for the rest of that row. We can also do the other edge of the scale here. So I'm going to erase these markings. Looking at these values here, the other extreme, if x is equal to 4, that means all of the cards are, I'm going to move my face over here. If x is equal to 4, that means all of the cards are ones. So it's pretty unlikely, but possible, that you would have a hand of all ones. And so then we're thinking about, okay, if all of them are ones, how many of them might be red? And so in that case, we just want to see out of all of the ones, remember there are 15 ones, 3 of them are red and 12 of them are non-red. And so if we want, for example, f of 4, 1, that's saying we want 4 ones, 1 of which is red. So that's saying we want 1 of the 3 red ones and 3 of the 12 non-red ones. Whew, all right. And again, always dividing by 52's 4. Similarly for f of 4, 2 and f of 4, 3. But you have to be careful, because here, this last value here, it's actually not possible to have x equals 4 and y equals 4 at the same time. Think about why that might be for a second before I tell you. Because every suit has 3 ones in it. 2 2s, 2 3s, 2 4s, and 1 5. So there are only 3 red ones in the deck. There's no possible way that you could have x equals 4 and y equals 4 at the same time. So that's why we have this 0 here. There are only 3 red ones. So we could get all of those, but then the last one, if it has to be a 1, it can't be red. And if it has to be red, it can't be a 1. So that's why we have that 0 there. That's not just like a rounded to 0, it's an actual 0. Like that combination, y equals 4 and x equals 4, is impossible. Let's do the other extreme now, down here. When y is equal to 4, that's saying that all the cards are red, and now all we're worried about is how many of them are ones. Are they red ones or red non-ones? So we can do that similarly for each of those 3 numbers. If we want f of 1, 4, that's 1, 1, and 4 reds. So that means one of them is a red one, and the other 3 are red non-ones. So there's 1 of the 3 red ones and 3 of the 7 red non-ones. And similarly for the other values, f of 2, 4 and f of 3, 4. Then I'm going to scroll back up for a second. Then we get to these numbers in the middle here. I've colored them all purple because they're all a little bit weirder to get. And I'm not going to talk through, I think, every single one of those calculations because it gets a little bit boring. But I am going to walk through 1 or 2 of them for you so you can see how these values come up. It gets a little bit tricky when we have multiple combinations because, again, of the fact that a card could be both red and a 1, or it could be a red non-1, or it could be a non-red 1, or it could be neither, a non-red non-1. So we sort of have 4 categories of objects, right? Like red 1, red non-1, non-red non-1, and non-red 1. I can't remember if I double counted, but there are 4 categories. I think of like dividing the space into those 2 attributes. All 4 combinations exist in the deck, and then these values want particular combinations of the numbers of each of those. So let's just try and calculate 1 or 2 of these purple numbers in the middle. I'm going to go to the next page. You can see how boring this is. I promise I'm not going to read through every single one of these calculations, but you get the idea. There's 9 values that we need to calculate. F of 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And so I'll just do the first one, and then you'll get the idea. So F of 1, 1 here, that means we have 1, 1, and 1 red. And there's multiple ways this could happen, right? We could either have one that is a red 1, so it satisfies both of those conditions at once in a single card, and then 3 cards that are neither of those things, so non-red, non-1s. There's 28 of those. Or we could have those 2 conditions, the 1 card being red and the 1 card being a 1, satisfied by 2 different cards. So that means 1 card has to be a red non-1, 1 card has to be a non-red 1, and the other 2 have to be neither. And so these 2 cases are mutually exclusive, so to find the probability of the both of them together, you just add them up. So again, each of those is calculated as follows. For 1 red 1, there's only 3 of those, and we want to choose 1 of them. For the neither, there's 28 of them, and we want to choose 3, and then we're obviously always dividing by 50, choose 4. For the other case, out of the 7 red non-1s, we want 1. Out of the 12 non-red 1s, we want 1. And then out of the 28 neither non-red non-1s, we want 2 of those. So that gives us our overall calculation. So again, I promise I'm not going to talk. It's a lot of symbols, I know. I would, it's just blah, my brain. Yeah, the crying, is that a crying sloth? I mood. So yeah, that's the idea. I could walk through all of these calculations, but I feel like it's pretty boring to do so. But the idea is you want to be really careful because here, even though there's only 2 attributes, red and 1, there's 4 possible combinations and each card falls into one of those categories. And so if you want exactly a certain number of 1s and exactly a certain number of reds, you have to think about what are all of the ways that that can happen. And again, sometimes there's multiple ways for that to happen. Sometimes there's only one way. So that's how all of these things are calculated. And you don't need to memorize these formulas or anything. There's nothing to do. This just gets us completing our table, which is great. So we have this table, all of these nice rainbow colors, and then what can we do with it? Once we have this joint distribution, we can look at all sorts of interesting things. We can find marginal distributions. So remember, for 2 discrete multivariate distributions, to find the marginal distribution of one, you just sum across all the values of the other. So for example, if we wanted the marginal distribution of x, which is the number of 1s, then we just sum down the columns. So collapse all of those columns into a single vector instead of a matrix, basically. And we get these values. You can double check that if you add up all of the column 0 values, you'll get that. And if you add up all of the column 1 values, you'll get that, etc. But the cool thing is that if you look at these numbers, this is identical to just a regular single variable hypergeometric distribution with these parameters. 50 cards overall, 15 are counting as our successes because x is the number of 1s and there are 15 1s, and little n equals 4 because you're choosing 4 cards without replacement and not caring about the order. So that's basically an intuitive result that when we collapse this table, we end up with a distribution that we're familiar with. And we can do it in the opposite direction. We can do the same thing. If we want to collapse the table this way instead, so sum across all the rows of this table, we will end up with these values, and you can double check that if you like. And again, this turns out to be a hypergeometric distribution with these parameters because the number of successes now for red cards is 10. There's 10 red cards in the deck. So that's kind of cool. We end up with these multivariable distribution that we got, but when we collapse it into either the rows or the columns, we end up with a familiar single variable distribution. Great. But I mentioned at the beginning that it's not just 2 hypergeometrics combined together, right? There are lots of matrices that could exist that when you squish down the rows and squish across the columns, you end up with these values. So we might be interested in knowing what the relationship is between these 2 variables, x and y. First thing we could think about is, are these variables independent? And I scrolled too far, spoiler alert, the answer is no. You can do that in a few different ways. One thing you could do is just choose your favorite value of x between 0 and 4 and your favorite value of y between 0 and 4 and check whether or not this relationship here holds. Does little f of xy equal little f sub x of x times little f sub y of y? If you find a single pair xy that violates this, that where this is not equal, then you know that the variables are dependent. Proving dependence is pretty easy. If you find a single value that breaks the equation, you're done. You can't have variables that are like halfway independent or anything like that. So one counterexample is enough. So we could take 0, 0, for example. If we take 0.2274 and multiply it by this number here, 0.3968, you will not get the same thing that's in our original table at f of 0, 0. It might be close, but it's not exactly the same. And if it's not exactly the same, that's enough. One single counterexample is enough to disprove independence. The other thing we can do is actually notice that there is a 0 in that column, the last row and last column that I talked about in the table. So because it's not possible to have 4 cards that are both red and both ones, they're all red and all one, that means instantly that we have dependence. So it's another really quick check for dependence. If there is a 0, if there's a 0 anywhere in your table, instantly you know that the variables are dependent. And that's because having a 0 means that one value of one random variable prevents the other variable from taking on a certain value. So knowing something about one random variable restricts the range of the other random variable. And that's dependence, right? Independence means they have no influence over each other whatsoever. Dependence is some influence in some direction. So in this case, because we have a 0 in the table, we know that the variables are dependent for sure, instantly, without even having to do any calculations. So that rule is actually a good thing to know. So in general, I'm going to add this. So if the joint range of two random variables is not a rectangle, or more formally, I guess you would say a Cartesian product of the sets, then they are definitely dependent. So that can be a really quick way to check for dependence. If you see a 0 in a table, then it's definitely dependent. One of the thought questions that I had posted on Piazza was like, there were some values like here, like a value here, 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 and then like 0, 0, 0, and like, I think like that, some value 0, 0, 0. So the joint range in that case was like this sort of triangle shape, and that's definitely not a rectangle. So you instantly know, without having to do any calculations, that variables like that are not independent. So then how could you use this information in the game, actually? Lots of different ways. Again, it's really not just a game about probabilities, because you're also like reading into what people are saying to you. You're getting more information constantly. But basically we could think about, what do we observe from the other player's cards? So if we like have our hand and we also see what else is going on, if we see somebody with like, someone has a red 1, and then like a couple of red non-ones and a couple of non-red ones and 7 cards that are neither red nor ones, we could then just update all of these probabilities with this information. And it might make a few more combinations of X and Y impossible, depending on, again, what we see, and it will update the probabilities of what we have. Now, I'm not saying that's what you should do when you're playing Hanabi. You should be having fun, but it's kind of neat that you can take this information into account. And it might mean, like, what you see might make certain combinations of what you have in your hand impossible. And also, as the game goes on, and as more cards have been played, you might be very, very sure of what you have in your hand at a certain point, because of being able to eliminate all of those other possible combinations. All right, so that's, again, a really neat game. It's a lot of fun to play, and really weird and tricky sometimes to try to tell people information without telling them, and not being able to see your own cards is frustrating, because sometimes you're like, oh, I just want to take a peek, but you can't, because it wrecks the game. Alrighty, okay, so then I want to talk about our machine learning idea of the week, which is another great one. This is known as the bag of words algorithm, and it can be used to analyze documents, to basically like try to determine whether or not they're spam or legitimate. Basically, what we're going to do is assume that the words in an email or a document of any kind are randomly drawn from a bag of words. And obviously that's not how emails work, but this is the base underlying assumption of this algorithm. And some words are going to be more or less likely depending on the content of the email or document. So again, if we theoretically knew that all of those probabilities of all the available words, and we know how long our email is, then the number of each word that we see in the email will follow what we call a multinomial distribution. And just to review that, if you either haven't watched the video or just watched it so long ago that you've forgotten, the multinomial is basically an extension of the binomial distribution. So remember, from the binomial, we have Bernoulli trials, which are independent, constant probability of success, and only 2 outcomes on each trial, success or failure. And then we define the variable to be counting up the number of successes. With multinomial, we keep those first 2 assumptions. Their trials are still independent, and the probabilities of each type are constant, but the third assumption gets relaxed. So instead of having only success or failure on each trial, we have multiple possibilities. So we have the k different possibilities on each trial, with probabilities P1 for type 1, P2 for type 2, etc., up to Pk for type k. And then we define not one random variable, but k random variables, one for each type, which are basically counting up how many times in these n trials did we observe type 1, how many times in these n trials did we observe type 2, etc. So we have like x1, comma, x2, comma, xk is going to be multinomial. And we need to know the number of trials, which we call n, similar to the binomial. And we need to know the probabilities of each type. So we have P1, P2, etc., up to Pk. Now, one thing for sure is that these x's are not independent. And that's one of those things that, like, people say, wait a minute, you told me the trials were independent. Well, yes, the trials are independent, but the number of outcomes of each type is definitely not independent. And I want you to think about why that is. This is one of the thought questions that I've now given away. They are most definitely not independent. To think about why that is, what if you knew that, say, x1 was really, really high, like really, really close to n? That means there were lots and lots and lots of type 1 outcomes in those n trials. And that means there are fewer possibilities for all of the other types. Like, all of the other types have to fit into that, because we know that x1 plus x2, etc., down to xk is equal to n. Each trial has to be exactly one of the k types of outcomes. And so if we add up the number of type 1s, the number of type 2s, etc., the number of type k's, we have to get exactly n, the number of trials that we do. So that means that the bigger x1 is, the smaller everything else has to be to some degree. And so that's a definition that means there's just some influence, right? What x1 is affects the possible values that the other variables can take on, right? If x1 is n, all the others have to be 0. If x1 is n minus 1, then all the other variables, only one of them can be 1, and all the others have to be 0. So there's some fairly strong influence going on because the sum of these variables has to add up to something fixed. So we know that these variables are not independent, but they do have this nice, what we call multinomial distribution. So how we're going to use this distribution is, again, to make this assumption that the words in this message are randomly drawn from a bag of words, where each of the probabilities of the words are different for each word. So let's say you got this email. Your account has been limited. Click here to reactivate your account. Seems legit. Maybe not. So let's say we then had a large sample of emails that were both legitimate and spam, which we would call a training set of data, and we could find the probabilities of these words. First, usually the bag of words algorithm is going to ignore words like the or to or or n or like you and stuff like that, just like words that come up too often that are really not informative. But let's just think about these words here: account, being limited, click here, reactivate, and then any other word in the world is going to fall into that other category. So let's say we had 2 different sets of data that this algorithm was trained on, a set of spam emails and a set of legitimate emails. And then we can see the probabilities of observing these words in each of those cases. So the probability if it's a spam message of each of these words is these values here. And then this is just the 1 minus the rest of them, right? This is just 1 minus the sum of those previous 7 values. Similarly, we would do the same thing with a large sample of legitimate documents, legitimate emails, and then we would end up with these probabilities. Notice they're quite a bit, most of them are quite a bit lower, and then this is 1 minus all of those. So we have these summing up to 1, this column sums up to 1, and this column sums up to 1, but the probabilities are not equal in the different sets. Right, like reactivate is a word that's not very commonly used in legitimate emails and more commonly used in spam. Other things like that. So if we have this data, that's great. What we can do then is figure out the probability of an email that looks like this. So we're going to try and find the probability of seeing the distribution of words found in this email if we knew ahead of time that it was a spam email. So what we can do is look at this email. We've got 11 words, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. Sorry, I covered it up. There we go. We have account appearing once, being limited, click here, reactivate account, and then how many other words? 1, 2, 3, 4 other words. So basically we have, again, 2 instances of the word account, 1 each of the next 5 words, being limited, click here, and reactivate, and 4 instances of other words that are like your, to, has, and your. So really common words. So what we would do is, again, theoretically, if these 11 words were randomly drawn from a bag of words with these probabilities, then the number of each of those that we see in this email would follow a multinomial distribution. Because we're drawing, again, from this like infinite bag of words, where you can draw with replacement, so you can have the same word more than once. Then each draw is independent, and we're counting up the number of each of those various types, or each of those various outcomes. So we have exactly the definition of a multinomial distribution. And so what we want then is, sorry, this is a mess, this formula here. We use the multinomial probability, joint probability function to calculate this. So we have f of 2 for account, 1 for being, 1 for limited, 1 for click, 1 for here, 1 for reactivate, and 4 other words. So if you remember the multinomial probability function, the joint probability function, is n factorial over x1 factorial, x2 factorial, etc., down to xk factorial. And then p1 to the x1, p2 to the x2, ... and then pk to the xk. And again, just to recap, the reason that that's the formula is these probabilities here are the probability of observing the correct number of each of those outcomes. So seeing outcome 1 x1 times is just the probability of outcome 1 multiplied by itself x1 times, etc. But then the orderings in which they can occur is those multinomial coefficients from way back in chapter 3. So if we have these n objects, and the orders in which they could come are calculated in this way. So we have, if we have multiple copies of words that are indistinguishable from each other, the number of ways they can be ordered is like this. So again, this algorithm is not taking into account the order in which those words appear. You could probably improve it if you wanted to do that. But here we're just thinking about what's the probability that in an email of 11 words, so in other words, in 11 independent draws from this bag of words, what's the probability that there will be 2 of them that set our account, 1 of the next 5 words, and 4 of the other words. So we can do that. We can sub these numbers into this expression. We get 11 factorial over 2 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, 4 factorial, but I've just left out the 1 factorials because they're just 1. And then each of these probabilities raised to the power of how many of them we want. So this is like the second probability in the list raised to the power of 1, etc., all the way down to the last probability here raised to the power of 4. Now this probability is absolutely tiny, like it's minuscule, because of course if we have a bag of words that contains like all of the words in the language that this is being done in, and you're drawing randomly from it, the probability of getting any specific result is very, very low. So the value of this being really, really small is not surprising. But it on its own is not particularly useful. What is useful is if we compare this probability to doing the exact same calculation if we use the legitimate probabilities instead. So we're going to do the exact same calculation, but subbing in the probabilities from the legitimate column instead. So here you can see instead of 0.0013, we have 0.0003 because the probability of a count appearing in a legitimate email is less than in a spam email. But all of the rest of it is the same idea. So all we've done is subbed in the updated probabilities from the legitimate column instead of the spam column. And the probability in this case is even smaller. So and we can compare them, right? Basically the word distribution in this email is 49.2 times more likely to have come from the spam bag than the legitimate bag. So that's kind of a really strong indication that this is probably a spam message. And that's kind of how this algorithm works. It's against a classifier, and this is a piece of evidence that you have in determining whether this is a spam message or a legitimate message. We could also do other things just for fun. The probability that an 11-word spam message has none of these words in it, that would just be taking this probability here, 0.9784, raising it to the power of 11, and taking 11 factorial over 11 factorial, and that's pretty high. So having being spam does not necessarily mean it's likely to have any of these words in it. It's the other way around. It's that having these words makes it more likely that it came from a spam set of words versus it came from a legitimate set of words. So that's it. That's how the bag of words algorithm works. It's kind of, again, fairly simplistic and actually relatively easy to understand now that we know about the multinomial distribution. We're, again, basically assuming that the words are randomly selected independently from a bag of words with different probabilities. And we can see then, if we analyze the likelihood of getting this particular set of words, if it's way more likely from one bag than another, then that gives us some evidence that it might be one type of message. All right. Someone asks, are we going to have a third computer-assisted assignment? And the answer is yes, of course. It was on the schedule, and I mentioned it in the checklist for this week. It's due on April 9th, and it's going to be posted today if it's not already up. And info about the final exam will be posted fairly soon. Someone asked, will it cover everything since the beginning of term, or will it only cover materials after the midterm? It will cover everything since the beginning, but there's likely a higher focus on the content since the midterm because we haven't had as much time to test that. Someone asked, I'm wondering if I didn't answer questions in Piazza because I didn't know the answers. However, I asked a couple of questions. Does that count as bad participation? No, not at all. There's lots of ways to get Piazza participation. Asking questions is a great way. Responding to questions, like answering questions, is a great way. But also answering the thought question polls or responding in comments to the sort of open-ended thought questions. So all of those are ways that you can get participation marks. Again, there isn't like a magic number of things that you have to do to get perfect, but if you sort of answered most of the polls, and there have been, I could figure it out, there's about 3 a week on average, so by now there have been about 30, but maybe not quite. So if you've answered most of those and responded to some of the either asked a question or responded to something maybe a few times a week, then you're in good shape. So thanks for that question. But yeah, if you don't know the answers to questions and therefore you're not answering other people's questions, that's okay. Similarly, if you don't have any questions and all you're doing is answering other people and you're never asking anything, that's also perfectly legitimate. So you don't have to answer and you don't have to ask. You just have to do one of those things, I guess, or comment on thought questions. And then those polls are going to still stay open. So if there's polls from previous weeks that you haven't answered, no worries. You can go back and do them now. Or you can actually, one thing that I might suggest is going back and answering all of them as you're doing your studying for the final exam. So answer, like put in your vote first before you peek at the comments, because a lot of them have follow-up discussions. And then once you vote, you can see the distribution of how everybody else voted. And 99% of the time, the majority answer is correct. In the couple of cases where the majority answer is incorrect, there's definitely a discussion going on in the follow-up comments. I have a question about multinomial distribution. Why don't we see a CDF for multinomial distribution? That is an excellent question. There's 2 reasons. One of which is I don't think in the notes we bothered to define maybe we did, a multivariate CDF. If we did, it would be something like big F of x1, x2, etc., up to xk. And it would be the probability that x1 is less than or equal to little x1, and x2 is less than or equal to little x2, etc., and xk is less than or equal to little xk. So that's what it would be. And so if you tried to graph that, it would be just, I can't even imagine it. It would be, instead of a step function, it would be in 2 dimensions, it would be like a series of planes. Basically, like a plane, and then at some point it would jump up to another plane, and then it would jump up to another plane. But if you go in different directions, it would jump up at different times. So it's very difficult to visualize. And also, the binomial doesn't have a closed form for the CDF. And so neither does the multinomial. Like only a couple, actually, only 2 of the discrete distributions that we've talked about have closed forms for their CDF, the uniform, the discrete uniform, and the geometric. So otherwise, we haven't been talking about CDFs because they don't have nice closed form expressions. You would just get them by summing up all of the values. But maybe I'm gonna go back to our table of of little f of xy. So if we wanted to know what's the probability, like big F of let's say 2, 3. So that would be the probability of x being less than or equal to 2 and y being less than or equal to 3. How we would get that is by summing up all of the little f of xy values that satisfy this, that have x less than or equal to 2 and y less than or equal to 3. So it would be the sum of, I guess, these 12 values. So if you added all of those up, that would be big F of 2, 3. And you can see that would get pretty messy. There's no closed formula that's going to really work for it. So that's a great question. And yeah, we don't usually talk about CDFs in discrete distributions to begin with. And so we don't usually talk about them in terms of discrete multivariate distributions. But there are joint, so multivariate continuous distributions. And in those cases, the joint CDF can be very, very useful. We don't talk about them at all in this course. We stop at the discrete case. But if you take stat 330 or 334, you'll see what happens when we have joint continuous distributions. You can kind of imagine what it's going to be like. Instead of having like double sums of things, you'll have double integrals of things. And for the marginal distribution, right, like to get the marginal distribution of x, right now we sum over all y. But in the continuous case, to get the marginal PDF of x, you would integrate over all y. So you can kind of think how that would work when we have 2 continuous distributions instead of 2 discrete distributions. It works fairly similarly, but it's not something that we cover in this course because I know most people haven't done double integrals yet, so we're not going to make you do that. So thanks for the question. Hopefully that answers it. It's just CDFs, especially in the discrete case and especially in the joint case, aren't usually mathematically tractable and aren't particularly useful, and they're hard to visualize. But in the continuous case, they are kind of cool. Thank you for tuning in. Have a great weekend. Remember to work on the second step, I guess, of your collaborative assignment. So checking out each other's questions. Make sure that each person's question is being done by 2 other people. That's important. And good luck with those. I'm excited to see them. I've been peeking at some of them and they look great. And I will see you next week, either on Thursday or Friday. I will make a poll on Piazza to figure out what the best time would be for you folks. Bye.